Hello, pre-calc. Welcome to section 3.3, chapter 3, part 3, on solving logarithmic, exponential, and logistic equations. So again, we'll take a look at solving our logarithmic and exponential. It's kind of a review of the last few years with a little bit of a extension to that. But then we'll look at the new part of logistic equations. So we'll start off and what we're going to do is we're going to have problems that have logs on one side and problems that have logs on two sides. So in other words, we have one log or more than one log. So kind of look at how we're going to do that. Well, if I do have one log, like I do on this one right here, we're just going to use the looping method to help us solve these problems. So, remember to put that little base in there so you remember. And then we'll just loop around to do this problem. So this will be 10 to the third equals that x to the third. And many times when we see this here, we're just looking and comparing this left side to the right side. And you can see if this is 10 to the third, this is x to the third, well then obviously the x has to be 10 for this answer. So what do you do when you just have one log? We'll solve by doing that looping method. All right. And what I would suggest for you if you have more than one log is to get it into one log. So by, let's see here, getting the equation or getting it into one log, and then loop. Kind of the key thing I just want to keep reminding you of always being aware of extraneous solutions to check these problems, that they do work. A lot of times what it'll do is it'll involve when it has a log as a negative number. So again, log can't be negative because if you remember the graph for log, it's got an asymptote here at x equals 0. It can't be over here. Can't have value. A negative value. So here we go. Let's get some practice doing some problems. So here we got just one log on one side. So really what I would just do is there's my base. I'd loop around and say this is 4 to the third equals that 4x minus 3. And then we can just solve this. 4 to the third is 64 equals 4x minus 3. And then you just got an algebra problem. So I add 3 and divide by 4. So 67 over 4. And again, just leaving things as reduced fractions is perfectly fine. They're actually the exact answers, so they're actually even better than doing some kind of decimal approximation, though this one would terminate. So the idea then is to try to get it into that single log, just have log base something alone on one side. So that's what we're going to want to do in this problem here, is to make sure that that happens. So just do some regular algebra, like subtracting 8. Always say, do the math you can do first. Just kind of consider this as just a regular algebra problem. So again, I'm trying to get the log of something alone. So this is 6 times that, so I'll divide both sides by 6. I have natural log of x minus 6 equals 1/6. And then again, remembering that natural log is really log base e, we can do our looping then. And this would be like e to the 1/6 equals x minus 6. And again, you could just add 6 to both sides. You have e to the 1/6 plus 6 is our answer. Again, you could just leave it like that. That's perfectly fine. All right, so we're just going to do a bunch of problems here. Just practice. These are our logarithm problems that we'll practice. So let's get a few more done here. So again, the idea here that we want log base is something alone. So I'm going to subtract 6 from both sides. So I have log base 5 of 8n minus 3. Subtract 6 from both sides, so you get 2. Now I can do my looping. This will be 5 squared equals 8n minus 3. So that's 25 equals 8n minus 3. Add 3, it's 28. Divide by 8. 28 over 8. And then if you simplify that, 4 goes into both those, so what's 7 halves? Okay. Let's just keep it rolling. Oh, hey, look at this. Wait a minute. There's logs on both sides. Logs on both sides. So if there's just one log on the left and one log on the right, really this is just, saying log of this equals log of this. So really we're just looking to see, are those two the same? Are these two things the same? In other words, when is a squared equal to that negative 2a plus 3? Because it's just log of this equals log of that. So we're just looking at those parts. Well, really, this is a quadratic, so all this comes back. So just set it equal to 0, a squared, then plus 2a minus 3 equals 0. And we could factor, so you can see all this prerequisite material always coming back. This is what, plus 3 and minus 1. So a equals 3 or a equals 1 are answers. And again, what I would say is just double check these to make sure they work. Oops, I'm sorry, that's negative 3. So if I put that in there, that'd be log of 9. And then over here, this is negative 2 times negative 3 was a positive 6 plus 9. So that works. Log of 9 equals log of 9. Put 1 in there. So that'd be what? Log of 1 equals log of negative 2 times 1 is negative 2 plus 3 is 1. Yeah, and that works too. So don't have any inappropriate answers here. We're not taking log of a negative number, so everything's good. So both of these work. All right, let's keep trying. We got some more multiple logs here. So here's where we can use some of those log properties. If I notice this is log of this minus log of that, well, remember the property for minus is we could write this as 1 log, and where we divide first one by the second one. And then I've just got a single log, which allows me then to do the looping method. So again, I'd say natural log is really log base e. And I have negative 5x minus 5 over 9 equals 4. And I could loop. So I'd have e to the 4th equals negative 5x minus 5 over 9. And then just clear those fractions by multiplying by 9 each side. So I'd have 9 e to the 4th equals negative 5x minus 5. And add 5. So 9 e to the 4th plus 5 equals negative 5x. And then divide everything by negative 5. So 9 e to the 4th plus 5 divided by negative 5. And you could go ahead and put that in your calculator if you needed a decimal approximation. But again, this final answer, that's what x is, so should be fine. Let's try another one. Again, get multiple logs this time on both sides. So again, we'll do this kind of like this one up here. We'll try to get a log on one log on each side, so then we can just kind of compare what they're doing. So let's just combine these two over here. This is they're all base 3, so this will be log base 3, and since that's minus, this would be 2 divided by x minus 10 equals log base 3 of 17. So again, since we got log base 3 of this equals log base 3 of this, we know that this piece and this piece should be equal. So we don't have to worry about the logs anymore. We just do 2 over x minus 10 equals 17. You can clear the fraction by just multiplying by that denominator. So you get 2 equals 17 times x minus 10. So 2 equals 17x minus 170. Add 170 to both sides. divided by 17. So what, 172 over 17. Again, that's perfectly fine to leave it as a reduced improper fraction. All right, let's move on to exponentials. Those are all logarithms. So move on to exponentials and solving those. So exponentials, again, have x's in the exponent. They are generally that form, y equals a times b to the x. So the idea is, when we solve these, is to isolate the term with the exponent first. And so when I look at this problem right here, 40 times 1/2, and this looks like this is, by blow that up a little bit, it's x raised to the x over 2 equals 5. So what we want to do is we want to isolate this piece right here. So is that not working? I thought the highlighter would work. So we're trying to isolate this piece, the piece with the exponent first. So really what that entails then is just me dividing by 40 on each side. So I have 1/2 raised to the x over 2 equals 5 over 40, which reduces to what, 1 over 8? And really now there's kind of two ways to kind of go about this problem. So I'm going to demonstrate both ways, and you can choose which way you like, and you might like one better than the other. But sometimes you can't do one in a certain circumstance. So what I'm going to do is, with this problem right here, one of the ways of solving this 1/2 raised to the x over 2 equals is to look at the term that's got the exponent and look at my answer. And what I want to do is I want to convert that 1 over 8 into some form of that 1/2. So that 1/2, so like 1/2 to what power is 1/8? Well, that's actually 3, because 1 to the third and 2 to the third is 1 over 8. Because then what that allows me to do is sort of like what we just did with the last problem, is if I've got the same base, really I'm just going to compare these pieces here. So it's just x over 2 equals 3 multiplied by 2, x equals 6. Now, that doesn't always work, because sometimes you get like maybe like a 1 over 7 where that doesn't jive. So this is a method over here that will always work. So if you're starting off with that 1/2 raised to the x over 2 equals 1 over 8, you can always rely on this method. And what that is if you want to solve for an unknown in the exponent, you just log both sides. So I get log of 1/2 raised to the x over 2 equals log of 1/8. And then we just start using our log properties in algebra to solve for this. So I can bring that x over 2 out front with the properties. So I can have x over 2 times log of 1/2 equals log of 1/8. And then I can divide both sides. So that x over 2 equals log of 1/8 all over log of 1/2. And then to clear this, multiply both sides by 2. So I'd have x equals 2 times log of 1/8 divided by log of 1/2. You'd have to type this into your calculator to get that answer, but believe me, when you do this, the answer does come out to be 6. So you can see, if you recognize that you can just change that that number over here to some base that matches, you can save yourself a lot of time. But again, that's not always going to happen. So you got to make sure you can go through this whole process over here. Okay, so let's go practice some other ones. And that's what I'll do right here. It's number 21 here. Again, the idea is to isolate the term with the exponent. So what I'll do is I'll just divide both sides by 18. So I'll have 1/3 raised to the x over 7 equals, and if I divide by 18 over here, that'd be 2 over 18, or reduced 1 over 9. So this one certainly is, if I look at 1/3 as the base, can I take that to some power to make it 1/9? Absolutely. So you got 1/3 is raised to the x over 7. The same, this 1/9 is 1/3 squared, because 1 squared is 1, 3 squared is 9. So now I've got these bases are the same, so I just really got to compare these pieces as the exponents. So x over 7 equals 2, multiply both sides by 7, x equals 14 is our answer. So it's always nice when that happens. Always nice when that happens. So let's see if it does it again. So let's here again isolate the term with the exponent first. So I got to get rid of that 6. So I'll divide both sides by 6. So I got 4 raised to the x over 3. 96 divided by 6 is 16. So 4 is my base. Can 16 be written as 4 to some power? It certainly can. 4 to the x over 3 equals 4 squared, because that's what 16 is. So again, I've got the same bases. So all I got to do is just compare the exponents. So x over 3 should be 2. Multiply both sides by 3. X equals 6 is the answer. Okay, but again, make sure you know this process over here for when you can't do that. Because this will work every time, no matter what that fraction is on the other side. But again, rely on the shortcut if you can do it. Got some more problems with exponents, solving exponentials. So let's kind of go ahead and look at this. Again, the idea still is to isolate the term with the exponent. So that means I got to get rid of this 7, so I'll subtract 7 from both sides. So I'd have minus 3e to the negative x. Subtract 7 there, I get negative 5. Then again, term with the exponent alone, so I get rid of this negative 3, so there's multiplying between that, so I'll divide both sides by negative 3. So that would be positive 5/3, because negative divided by negative is positive. Now, this is one where, again, you can't look at this. This is not, e to the negative x. This is not e. It doesn't work out real well. So now here, this is where you'd have to take the log of both sides, like we did in this problem right up here, taking that log of both sides. But here's my tip as well, too, to make life a little easier, is if there's an e in the problem, don't take the log of both sides, take the natural log of both sides. You'll see why here in a second. So again, I took the natural log of both sides. I can bring that out front to that exponent. So I got negative x times the natural log of e equals the natural log of 5/3. And then here, this is why we do this, because the natural log of e is really like log base e of e. And from our properties, when these are the same, my answer is just whatever this exponent is here, which is 1. So the natural log of e is 1. So this just makes this negative x equals natural log of 5/3. And then to solve for x, well, I just want the opposite. So negative natural log of 5/3. And you can leave it like that, or if you need the decimal approximation, go ahead and type that in your calculator. So let's do it again. Let's give it a try here. Keep practicing. So again, I want to isolate the term with the exponent first. So I'm going to subtract 37 from both sides. So I'd have 2e to the negative x equals 37. I want to still get that term alone, so I get rid of that 2. So I'll divide both sides by 2. So I'd have e to the negative x equals 37 over 2. And then again, now I see there's an e in the problem. Again, I can't really look at this e in the base there. That's really not going to work for me to do the simple little part of the problem. So again, I'll take the log of both sides, but again, because I see an e, I'll do the natural log of both sides. And then again, I can bring this out front. So this would be negative x times the natural log of e equals the natural log of 37 over 2. Again, natural log is 1, so you have negative x equals natural log of 37 over 2. Again, I want the positive x, so I'll just take the opposites. And this would be fine for your answer. If you need a decimal approximation, yeah, you go ahead and type that in your calculator. So there's exponentials, solving exponentials. Let's get into solving logistics, solving logistic equations. So let's shrink that up a little bit, fit that on the screen. And again, here's our basic form for our logistic equation. Again, where that C is that limit, excuse me, yeah, that we're looking for. And we'll just start going into the problem here. So here, the high school has 1,500 students. So that's going to be our limit. Okay, so that's going to be the top number in our problem here. So that C is right there. So that's our C value that goes right there. It says 5 students start a rumor. Okay, so 5 students are starting this rumor. And which spreads logistically so that here's our equation. Let me write that a little bit bigger for us over here. So we'll write it as S of t equals 1,500. So you can see that's why they wrote that. That's that number right there. That's our limit there. So 1 plus 29e, and I believe that's a small printing there, negative 0.9 t. Right. So it says this models the number of students who have heard the rumor by the end of t days, okay? Where t equals 0 is the day rumor begins to spread. So the question is, how many students have heard the rumor by the end of day 0? So that's what we're looking for. And using this formula for part A is we're just looking for S of 0. So let's just substitute that into the equation and figure this out. So you got 1 plus 29e to the negative 0.9 then times 0 up in that exponent. All right. Well, as we keep breaking this down here, this is what, 1,500 on the top. 1 plus, now the 0 times here would just be 0. E to the 0, anything to the 0 is 1. So 1 times 29 is 29. And we got 1,500 over 30. And cancel the zeros. 150 divided by 3 is 50. All right. So in part A, how many students have heard the rumor by the end of day 0? Well, we've got 50 students that have heard that rumor by the end of day 0. Part B is asking us how long does it take for 1,000 students to hear the rumor? So there, this 1,000 students is already the total. That's this value right here. So that's how we're going to solve this problem, is we're going to put 1,000 in for the y value here. So 1,000 equals 1,500 divided by 1 plus 29e to the negative 0.9 t. So here we go. Again, what I would probably do is, again, don't like the fractions, so I clear those fractions. So I just multiply by 1 plus 29e to the negative 0.9 t in both sides. So that 1,000 times 1 plus 29e to the negative 0.9 t equals 1,500. And then just doing some algebra here. Again, remember, we want to isolate the term with the exponent and get rid of everything else. So then we can solve using our logs. So divide both sides by 1,000. So this would be 1 plus 29 e to the negative 0.9 t, and then 1,500 divided by 1,000 is 1.5. Subtract 1 from both sides. So it's just kind of doing your little algebra tools here. So subtract 1, that's 0.5. Oops, that's sloppy. And then divide by 29. So you have e to the negative 0.9 t equals 0.5 divided by 29. So now I've got this isolated. Again, you can't really see with those bases, so we're going to take the log of both sides. But again, I see an e, so I'll do a natural log of both sides. So natural log of e to the negative 0.9t equals the natural log of 0.5 over 29. Bring this out front, so you have negative 0.9t times the natural log of e equals the natural log of 0.5 over 29. This is 1, so I've got negative 0.9t equals the natural log of 0.5 over 29. And then I'm just dividing by negative 0.9. So t equals the natural log of 0.5 over 29. Clear that up a little bit. All divided by that negative 0.9. So we were actually looking for how long does it take for 1,000 students to hear the rumor. So now we probably do, in context, want to make sure that we take this, type that into a calculator, and get an approximate answer. So t, when you do this on your calculator, you can check me on this, but should get about 4.5. So then the question is, what is that t representing? And remember now the t was the days. So this is 4.5 days 1,000 students will have heard the rumor. All right, let's keep going. Let's look at another problem here. We want to look at the spread of the zombie infection in a small town. It's modeled by this logistic function. T is the number of infected zombies, and time, T is the time in days. So we're going to remember that piece too. The time was measured in days. So many people live in the town. Well, that's kind of a straightforward answer because that's just our limit to growth right there. That's 788. So pretty quick answer to that question. Letter B says, how many zombies were there initially? Okay. So that's what we're looking for then is z at time 0. So I'm putting 0 into that t value. So let's do it. 788 all over 1 plus 16 e to the negative 0.8. I'm putting 0 in for that t. If I do that, I get 788 over 1 plus, and then 0 times this is 0. E to the 0 is 1. 1 times 16 is 16. So it should be 16. So I still got to add this. This is 788 over 17. So how many zombies were there initially? This comes out to, I think about 46.35, proper rounding rules, because we're talking about zombies here. Some people would argue you could have a part of a zombie still out there, but there's only 46 full zombies. Now, there isn't a question here, but I'm going to add that in. I'm going to add in here a letter C for this one and ask you, how long until half the town is infected? So half the town. Well, half the town would be, if I'm looking at half of this, so 788 divided by 2 is what, like 394? Yeah. So I'd have 394. I'm looking to see, when do I have 394 people infected? So that's putting that into the equation on this part. And we'll solve for t here. So 788 over 1 plus 16 e to the negative 0.8t. And that's what we're going to solve for, is we're going to solve for that t. So again, I don't like fractions, so let's multiply both sides by that to clear that out. So we'd have 394 times 1 plus 16 e to the negative 0.8t equals 788. Divide both sides by 394, so I'd have 1 plus 16 e to the negative 0.8t equals 2. Subtract 1, negative 0.8t equals 1. Divide by 16, so I'd have e to the negative 0.8t equals 1/16. So again, now I've got the term with the exponent isolated. So here I got e, so I'm going to take the natural log of both sides. Natural log of this side. Come back up here, get myself some more room. So I can take this exponent and bring it out front now. So that'd be negative 0.8t times the natural log of e equals that natural log of 1/16. This again is 1. So I got negative 0.8t equals the natural log of 1/16. And then just divide. So t equals the natural log of 1/16, all divided by negative 0.8. So you type that into your calculator, and I believe it comes out to be roughly about 3.5 when I checked. So again, this is, remember the T stood for days. So when will half the town be infected? In roughly 3.5 days. So there we go. There's examples of solving logarithmic equations, exponential equations, and logistic equations. So you got some work to do, and as always, we'll answer any questions you got in class. Thanks, everybody.